In this physics tutorial, you will learn 1. The meaning of equal, opposite and different vectors. 2. How to add and subtract two or more vectors in a straight line. 3. The two rules of vectors addition when they are not in a straight line. 4. To express the difference of vectors as the sum with the inverse. 5. To add or subtract vectors using coordinates. Introduction. In the previous physics tutorial we discussed vectors and scalars in physics. We covered the properties of a vector such as its module, components, direction, determined by the angle to the horizontal direction, and the respective trigonometric functions stemming from it. Also, we discussed about the different approaches of maths and physics when dealing with vectors. However, the discussion was concentrated only about a single vector quantity. But what happens when two or more vector quantities act together in the same object or system? For example, if two or more people pull the same object, if two or more displacements are combined together, etc., you will know the answer after reading this article. Equal, opposite and different vectors. 1. By definition, two vectors are equal when they have both the same magnitude and direction. When they are parallel, look at the figure on screen. 2. Two vectors are opposite when they have equal magnitude but opposite direction. When they are anti-parallel, look at the figure on screen. 3. If two vectors are neither equal, nor opposite, they are different. This includes the cases when vectors, 1. Have neither equal magnitude nor the same direction, 2. Have equal magnitude but different direction, and 3. When they have the same direction but different magnitude. The image on screen provides an example from each of these cases. Addition and subtraction of vectors in a straight line. The meaning of resultant vector. This is the simplest case of the vector's addition. For example, if two horses are pulling the same cart, there are two forces acting in the same direction although the application point is slightly different, figure 4. On the other hand, when two groups of people are playing the rope pulling game, we have again two forces acting in a straight line but in opposite direction, figure 5. It is obvious that we must combine the vectors to calculate their overall effect. This effect is known as resultant of two or more vectors. Thus, the resultant vector represents either the sum or the difference of two or more vectors acting on the same object or system. The resultant vector is a single vector that virtually replaces the actual vectors and gives the same effect in the object or system. It is often denoted as V net vector, as well. V is a generalization. It may represent any vector quantity. In the first case, figure 4, we have to add the vectors, and in the second, figure 5, we have to subtract them. Therefore, the resultant force vector in these two cases is as shown on screen. Thus, the first equation is an example of vectors addition and the second one, an example of the vectors subtraction. In few words, if we add two vectors in a straight line, the result is a new vector whose magnitude is equal to the sum of magnitudes of each single vector, and if we subtract them, the result is a new vector whose magnitude is equal to the difference of magnitudes of each single vector. In algebra, there are not four basic mathematical operators, addition, subtraction, multiplication and division, but only two instead. They are addition and multiplication. Subtraction is considered as addition with the opposite and division as multiplication with the inverse. For example, this is true for vectors as well. Thus, if we set a positive direction, usually the right side, but it is not necessarily meant to be so, the opposite side will be the negative. In the second figure shown on screen, if we consider f right as positive, then f left will be negative. Therefore, instead of writing, we can write Therefore, to avoid confusion, it is better to forget the subtraction of vectors, and whenever there is a situation involving vectors with opposite direction, consider it as addition with the negative. Example 1. 3 electrically charged objects are placed in a straight line as shown in the figure on screen. The magnitudes of electric forces acting on the second object are as shown on the text on screen. Calculate the resultant force acting on the object 2, considering the rule, like charges repel each other while unlike charges attract each other. Solution 1. Giving the previously mentioned rule, it is easy to deduce that the object 2 will be attracted by the object 1, and it will be repelled by the object 3. Therefore, both forces acting on the second object will be oriented due left. Therefore, the magnitude of the resultant force, net force, acting on the object 2, will be the sum of the magnitudes of the two forces. Thus, it is clear the direction of the net force will be due left as well. Addition and subtraction of vectors that are not in a straight line, are not linear. When vectors do not lie in the same line, it becomes more difficult to find the resultant vector. However, we can use the concept of components to ease the calculation of the magnitude and direction of the resultant vector. But first, you must know the two techniques used to draw the resultant vector. They are the triangle, tip-to-tail, rule. Basically, this rule consists on placing the tail of the second vector to the tip of the first one. Even if the vectors are distant, we can use the method of parallel transportation of these two vectors at a new place in which we can put them one after another as required. Look at the figure. Thus, if we have two vectors A and B, and we apply the tip-to-tail rule as shown in the figure, the vector C, which starts at the tail of the first vector A, and ends to the tip of the second vector B, C, would represent the vector sum of the two previously mentioned vectors. If we are asked to draw the vector difference, D, of the two vectors A and B, shown in the figure on screen, we simply revert the second vector B, and then apply the addition rules based on the algebraic law of subtraction. The parallelogram, tail-to-tail, rule. According to this rule, if we put the two vectors A and B at the same starting point, tail, the resultant sum vector will be the diagonal of the parallelogram formed by these two vectors. We draw other two sides that are in parallel to the given vectors in order to form the parallelogram. Look at the figure on screen. As for the difference, we revert again the second vector B, to obtain the vector minus B, and apply again the parallelogram rule for the addition of vectors. Look at the figure on screen. We can deduce two conclusions from the previous figures. The vector sum, C equals A, plus B, is the same in both methods, shown on figure 6 and 8, and the vector difference, D equals A, minus B, is the same in both methods as well, shown on figure 7 and 9. Whatever method you choose, it gives the same result. If the vector sum gives the diagonal of the parallelogram formed by the two vectors and their parallel extensions, shown on figure 8, the vector difference gives the other diagonal of the same parallelogram, shown on figure 9. Addition and subtraction of vectors in coordinates. As discussed in the tutorial Vectors and Scalars in Physics, a vector can be projected on a 2, or even 3-dimensional system of coordinates. If we denote the vector as A, B, where A is the tail and B is the tip position, it is obvious we have two pairs of coordinates representing the vector A, B. They are X, A, Y, A, X, b and y, b, respectively. Therefore, the equations for the horizontal delta x, and vertical shifts delta y, of the tip in respect to the tail are as shown on screen. In this example, we have x tail equals x, a, equals 1 unit. X tip equals x, b, equals 4 units. Y tail equals y, b, equals 2 units. Y tip equals y, b, equals 4 units. Hence, therefore, it would be better if we carry in parallel the vector a, b, and put the tail to the origin to avoid the use of 4 coordinates. We need only 2 coordinates, the new coordinates of the tip, as the coordinates of the tail now both become 0. The visual expression of this concept is shown on screen. Here, the values 3 and 2 show the components a, b, x, and a, b, y, of the vector a, b, when its tail is placed at the origin. Therefore, we can only consider the horizontal and vertical shift of the tip to the tail, regardless the position where the vector is. In this regard, if we want to add 2 vectors when the coordinates are given, we can simply add mathematically the respective components. The same is also true for the subtraction of vectors. We can simply subtract the corresponding coordinates to obtain the coordinates of the vector difference, or add with the opposite. The mathematical rules for the addition and subtraction of vectors are as follows. In the graph previously shown, delta y, a, b, is negative, whereas y, b, is greater than y, a. This means that the resultants, delta x, total, and delta y, total, do not necessarily represent the mathematical sum of magnitudes of the corresponding vector components. After putting the vector a, b, at the origin and the vector c, d, at the tip of a, b, we obtain the following figure for the vector sum a, d. Hence, it is obvious the vector sum is obtained by adding the components. The same occurs for the vector difference. It is obtained by subtracting the components of the second vector from those of the first one. The new coordinates obtained represent the vector difference. This rule is valid for the sum of more than 2 vectors as well. As for the difference, you must change the sign and the coordinates of the second vector for each pair of vectors that needs to be subtracted and then finding the sum instead of difference. Example 2. An object moves linearly from the origin of the coordinate system to the position 7 meters, 14 meters. Then it changes direction and moves linearly for other 1 meter due west and 6 meters due south combined together. Calculate the total displacement of the object in meters. Take east and north as positive directions. Solution 2. Since east is positive, the final horizontal coordinate of the object will be as shown on screen. And its final vertical coordinate will be. Therefore, since the object was initially at 0 meters, in order to find the total displacement, delta r, we have to calculate the magnitude of the vector whose tail is at 0 meters, and whose tip is at 6 meters, 8 meters. Hence, we have. The figure is shown on screen. Summary. By definition, 2 vectors are equal when they have both the same magnitude and direction. When they are parallel, 2 vectors are opposite when they have equal magnitude but opposite direction, when they are anti-parallel. When 2 vectors are neither equal, nor opposite, they are different. This includes the cases when vectors 1, have neither equal magnitude nor the same direction, 2. have equal magnitude but different direction, and 3. when they have the same direction but different magnitude. The resultant vector is a single vector that virtually replaces the actual vectors and gives the same effect in the object or system they act. It is often denoted as V, net, or net vector, as well. V is a generalization. It may represent any vector quantity. If we add two vectors in a straight line, the result is a new vector whose magnitude is equal to the sum of magnitudes of each single vector, and if we subtract them, the result is a new vector whose magnitude is equal to the difference of magnitudes of each single vector. When two or more vectors do not lie in a straight line, we use two basic rules to find their sum. They are the triangle, tip-to-tail, rule. Basically, this rule consists on placing the tail of the second vector to the tip of the first one. Even if the vectors are distant, we can use the method of parallel transportation of these two vectors at a place in which we can put them one after another as required. The resultant vector starts at the tail of the first vector and ends to the tip of the second vector. The parallelogram, tail-to-tail, rule. According to this rule, if we put the two vectors a and b at the same starting point, tail, the resultant, sum, vector will be the diagonal of the parallelogram formed by these two vectors. We draw other two sides that are in parallel to the given vectors in order to form the parallelogram. The same rules can be used for the difference of two vectors as well. We must simply upturn the second vector and then use the addition rules. If we want to add two vectors when the coordinates are given, we can simply add mathematically the respective components. The same is also true for the subtraction of vectors. We can simply subtract the corresponding coordinates to obtain the coordinates of the vector difference. The mathematical rules for the addition and subtraction of two vectors, a, b, and c, d, are as follows. This rule is valid for the sum of more than two vectors as well. As for the difference between more than two vectors, you must change the sign and the coordinates of the second vector for each pair of vectors that needs to be subtracted and then finding the sum instead of difference.